So students, last time we have touched upon the MOSFET capacitance. So let me revise in the first 10 minutes. MOSFET capacitance. So if you have not drawn the diagram, you can draw along with me right now. Alright, so let's start drawing the MOSFET capacitance. Leave some space at the top and draw this diagram at the bottom. So we have the gate, then we have the oxide layer below. So this is my oxide layer below. Then we have the P silicon substrate. So this is my P silicon substrate. Okay, I have the source and the drain region over here. This is my source, this is my drain region, N plus source, N plus drain. Okay, and the body terminal is over here also. This is P plus. So let me mark the terminals now. This was the gate terminal. Gate that's the source. This is the body terminal, which we normally connected to the lowest potential for NMOS, which is ground. This is my drain. Okay, so this is my gate terminal made up of metal or polysilicon. So this is my gate, and this is my oxide layer. This is my oxide layer, which I am marking with dots. Alright, I am not marking it, but this is my metal oxide and this is my semiconductor. Okay, now proportional to it, we will draw the top view. So this is the cross sectional view of the MOSFET. This we call it as cross sectional view of the MOSFET, of the N channel MOSFET. So of the NMOS. Now we have to draw the top view of the NMOS. So for the top view, we will take these dimensions of this gate. Okay, so let me take the dimensions of the gate and draw this. This is from the top view. Alright, and then I'll extend on right hand side and left hand side these things. So from here to here. Pardon, on the right hand side is slightly bigger, but it's symmetric. Consider it as a symmetric. Okay, now where is my source and drain? This is my source region from here to here. Alright, so let me mark it in green color. So this is my, if I draw this dotted line over here, somewhere around here it will be my N plus source, and it will extend up till here. It goes inside the gate, overlaps slightly with the gate. Okay, this is N plus source. Similarly over here we have N plus drain, so it goes up till here. We are drawing the top view of this. So from the top view, how it will look like. So this is N plus drain. Okay, now what is my actual channel length? My actual channel length, if I want to show it over here, it will be from here to here. Yes or no? This is my channel length. So in this case, in our case, this is my channel length L. Okay, this is my channel length. This length we call it as a gate length. So this we call it as LM, the total gate length. Then this small overlap, do you see over here? This is a small overlap. This we call it as LS, overlap at the source, and this also here it is small overlap. This we call it as LD. Okay, so if I want to write hypothetically what is L, how can I write it? So capital LM is equal to L plus LS plus LD. Yes or no? And normally due to the symmetricity of the MOSFET, LS and LD are same. So how can you write L? L will be LM minus twice LD, let's say. Okay, so L is my channel length. So this is my channel length. So some part of it is overlap with the overlap length, which is LD and LS. Okay, so this is actually my top view of, this is my top view of NMOS. So just pardon me to draw this slightly again. This I have taken, yeah, I think up till here it's fine. This is extra. So this will be slightly symmetric. So I've drawn up till here. Okay, so normally what we connect over here is we connect a N plus implant, sorry, P plus implant here like this, because if I want to connect an adjacent MOSFET, there will be a illegal channel formed between this N plus and this N plus. So to prevent that, we have connecting here P plus implant. So this is called as P plus area. Here also we have a P plus, so that anything connected to the left or to the right adjacent of this MOSFET does not create a illegal channel formation. Okay, so this regions are called as channel stop implant, here, over here and over here. So this is called as channel stop implant. Okay, so this is my top view of the MOSFET. Here also two more things are there. You know, I have the, this is just the front view of the MOSFET, right? So if I go in depth like this, so there will be my channel length also like this, right? So it will be like this, right? So this length will be my channel length L, W. Okay, so here how will I show W? What is my W? This is my W here, this is W. Okay, now one more thing is there, this is Y. From here to here, from here to here it is Y. I'll tell you what is Y and all everything. So LM is the mask length of the gate, LM is the mask length of the gate, L is the actual channel length, LS and LD are the drain and source overlap region length. Okay, so L we have written over here as LM minus twice LD, provided that LD and LS are same, the overlap area is same. So how much is this? Almost, let's say if L is around 180 nanometer, LMS will be around, let's say, 182 nanometer. This LD is around 1 nanometer, very small overlap, very small part of it is overlap. Here we have shown a little bigger, so for over exaggeration. W is the source and drain diffusion region width. Okay, say source and drain diffusion region width. What is Y? Y is called as diffusion region length. Diffusion region length. So the width of the N plus diffusion is W, the Y is the length. Agree? And there is one more thing, one last thing is there, XJ. So you'd see this height of this, depth of this junction, this N plus junction from here to here, we call this as XJ. So what is XJ? Source and drain diffusion region depth. Okay, so it's diffusion region, this is called as N plus diffusion region, diffusion region depth. Okay, just a quick check, you are able to hear me clearly and able to view the diagrams clearly, everyone? Yes or no? Just a yes or no?
Yes, sir.
Okay, now the reason for the channel stop implant I have already informed you. So both the source and drain regions are surrounded by P plus doped region. This is done to prevent the formation of any parasitic or unwanted channel formed between the two neighboring MOSFETs. Okay, or it's basically to electrically isolate the neighboring devices, built on the same substrate, because normally we take this silicon substrate only. p silicon substrate. Okay, so this is my this is called as source diffusion region. This is called as drain diffusion region. Okay, I hope it is clear. So this I have drawn the 3D view. I hope this is also clear. This, let me just remove it. Okay, or else it will complicate the things. Alright, now I will be telling you all one by one by the classification of MOSFET, what type of MOSFET they are present over here. So let's start with the MOSFET capacitance types. So these are all on-chip MOSFET capacitance. So on-chip MOSFET parasitic capacitance types. So if they ask you in the exam, you can write this types also as it is. So first of all, they are classified into two types. One is gate oxide related capacitance. Gate oxide related capacitance. Other is junction capacitance. Now this junction capacitance are related to the PN junction capacitance. I'll give you an example. So let's say if you have a PN junction. Now whenever you have a PN junction form, there will be a formation of a depletion layer, yes or no? So let's say this is my P and this is my N, and I'm reverse biasing it. So what is the function of reverse biasing? I mean, if we increase the voltage from 5 to 10, what will happen? The channel, the depletion region will increase, yes or no? So this is my depletion layer which will increase, depletion region will increase. So what is happening is, here we have P side, here we have N side, and separated by an dielectric which is changing. Okay, so we have a formation of a capacitance. So capacitance is epsilon A by D, right? In this case, D is the depletion region. Okay, let's say this is XD. Okay, so C is actually inversely proportional to XD, which is my distance. So same thing is happening, as my increase my reverse bias voltage, my depletion layer is increasing and my XD is increasing. So if XD is increasing, what happens to the PN junction capacitance? It decreases. So there is a PN junction capacitance which is present in the reverse bias condition. Okay, so in a reverse bias, your PN junction diode acts as a capacitor because it stores the immobile charges in this PN junction, right? So same way, and of course area, if we consider on this side, it will be capacitance per unit area, like this. So now it will be depending upon the dielectric of the material and the distance between the two plates. So here this unit will be farad per centimeter square, and this is what is junction capacitance. This is what is junction capacitance meaning. Okay, so this is present in PN junction, correct? Now we can have, instead of PN junction, we can have P plus N plus junction, right, or something like that. So now let us see its PN junction origin in the MOSFET. Now let me also connect my just a second, let me connect my laptop to my charger once, so that I don't get any disruption in the connections. Yeah, I hope my laptop is started charging. Yeah, okay. So are you understanding the PN junction junction capacitance which are there present? Okay, now where is this PN junction over here? So we are talking about now only junction capacitance. Where is this PN junction? Do you see any PN junction over here? Tell me fast. Do you see any PN junction over here? Yes. Which is the PN junction? Here, this one. This N plus. Okay, and this is my P. So there is one PN junction over here. There is one PN junction over here present also. Yes or no? This is p silicon substrate. This is made up of p silicon substrate, and this is made up of n plus. So this is a p n plus junction. Here also we have a p n plus junction. So because of these this p n plus junction, let me just rub this out. We have two junction capacitance because this is a p-n junction form, right? P-n plus junction, p-n plus junction. So because of that, we have two capacitances which are called as C S B J. So how do we read it? Source to substrate junction capacitance. Source to substrate. B stands for body or substrate. So source to substrate, J stands for junction capacitance. And here there is one more. C D B J. This is called as drain to substrate junction capacitance. Okay, or drain to body junction capacitance. So these are two, um, you know, area capacitances. Area capacitances. So let me mark it over here. So there are two types for junction capacitance, which are, first is area capacitance, whose unit is farad per centimeter square. As I've informed here, see, if I write capacitance per unit area, it depends upon the dielectric and the distance. For the PN junction, for this PN junction, we will write it. So this will be capacitance per unit area. That will be depending upon the dielectric of the silicon and the distance between the two plates, which will be d, which we'll be seeing now very soon. So here area capacitance are of two types. One is CDBJ, drain to substrate junction capacitance, and second is source to substrate junction capacitance. Okay, both of them have the value unit as farad per centimeter square. Then there is two more capacitances which are present, which are called as side wall capacitance. It's not related to the area, it depends upon the periphery. So unit is farad per centimeter only. Okay, so there are two more PN junctions present. So if you see carefully, which are the two PN junctions present over here now? If you see, this is also a PN junction, right? Here, correct? And here also we have a PN junction. This is P, this is N. So that is also reverse bias. Yes or no? Because body is grounded and your drain is connected to positive. So this becomes PN, this becomes reverse bias. So these capacitances which are present between these two junctions are, let me mark it. So there are capacitance present over here. This is called as CSWSJ, and this is one more capacitance over here, which is called as CSWDJ. Okay, so what is CSWDJ called as? It's drain to substrate sidewall capacitance. Drain to substrate sidewall capacitance, and here it is drain. SW stands for sidewall. Source to substrate sidewall capacitance. Okay, source to substrate sidewall capacitance. Let me add it over here. So you have two more over here, which is CSWSJ, source to substrate sidewall capacitance, and here it is CSWDJ, which is drain to substrate sidewall capacitance. Okay, now both of these capacitances are voltage dependent. Okay, it depends upon the applied reverse bias voltage. So these are, both of them, area and sidewall capacitance, are voltage dependent capacitance. Voltage dependent capacitance, or it depends upon the large signal switching. It depends upon the large signal switching, which is large change in the voltage. Okay, so this is about the junction capacitances. That's why the suffix we have J everywhere. So CDBJ, CSBJ, CSWDJ, and CSWSJ. So these are all junction capacitance divided under area and sidewall capacitances. Okay, now here, in case of gate oxide related capacitance, there are again two types. One is gate overlap capacitance and other is gate parasitic capacitance. Okay, so gate overlap capacitance, we have two types. Let me just mark it over here first. So you see, gate is drain and source region are slightly overlap with the gate region. So because of that, you see this is the Tox. This distance over here is Tox. Here, this one, this thickness is Tox. Okay, so between the gate terminal and the N plus substrate terminal and N plus source region over here, we have one capacitance called as here because of the overlap. This is CGS, gate to source overlap capacitance, and there is one more here because of the overlap. Okay, this is CGD, gate to drain overlap capacitance. This is because of the overlap region between the source and the drain with the gate. Okay, so these two capacitances are present over here. Alright, so let me mark it over here. Gate overlap capacitance are of two types now. What are they? CGS, which is gate to source overlap capacitance, and CGD, capital. Remember, we have written capital. So these two capacitances are lumped capacitances, meaning they cannot be distributed, and these capacitances are independent of voltage. Independent of voltage because they are present because of the gate and so drain and source overlap with the gate. Okay, and this unit is farad. Okay, so area is already into consideration. So the unit of these capacitances are farad. Okay, so now tell me, in the oxide layer, what is my capacitance is present? So we have to determine what is CGS. What is my capacitance in the oxide layer? Cox, yes or no? Hello, you are able to hear me? So Cox is the gate oxide capacitance given by epsilon Ox upon Tox, that is there, right? Now we have to determine what is CGS. CGS. So CGS is Cox multiplied by area. Okay, so Cox, it will be the gate oxide capacitance multiplied by area because it is in farad. So what is the area over here? Overlap area over here. So here we have LS or LD, because both are the same. Okay, and what is the width of this N plus region? It is W. Okay, so the area over here will be, area of this will be a strip like this. It will be a strip. Yes or no? Where this length is LD or LS, and this is width W. So what is the area of this rectangle? Can anyone tell me? Length into width. So what is the area? Hello, please let me know the area of this strip. Cox into, you all are there present in the meeting. Someone can confirm what will be the area? Hello, what will be the area of this strip? Come on, tell me. So how will I understand whether you are following or no then? Sorry, can you say again?
W into LD.
Yeah, W into LD or LS. So that's correct, CGS. And similarly CGD, it will be Cox W into LD, which is the area. So therefore the unit will be in farad. So CGS and CGD is the gate to drain and gate to source overlap capacitances, and they do not depend upon any voltage, as you can see. They are present just because of the structural, the way it is connected. The n plus and n plus source and drain diffusion region, they are overlap with the gate. That is why these capacitances are present. Alright. Okay. Now we go on to the last category of MOSFET capacitance, that is gate parasitic capacitance. There are three types over here. So there are three types over here. Which are the three types? I'll write it down. CGD, CGB, CGS. This CGS is small. That means it is gate parasitic capacitance. Okay. So this is gate to source parasitic capacitance, gate to substrate parasitic capacitance, gate to drain parasitic capacitances. Okay. And these capacitances are distributed capacitance. They spread over the channel. Distributed capacitances. They depend upon the region of operation of the MOS device. So depends on region of operation. Like which are the region of operation? Cutoff, linear, and saturation. So it depend upon the region of operation of the MOS device. Let me highlight them over here in this. Okay, so here right now I'm just showing this capacitances in here. So this is CGS, CGS, then one is CGB, another is CGD. So these are the three capacitances which are present. Parasitic capacitances: gate to source, gate to body, and gate to drain. Alright, they are present because of the the availability of the n channel, non-availability of the n channel, and so on and so forth. So they are distributed across the gate length. Okay, CGS, CGB, CGD. So let us understand how they are distributed. Okay, in terms of the the different modes of operation. So let us try to understand that now in brief. Okay, so in the cutoff mode, what is my situation of the channel? Can you tell me? So we have n plus, in the cutoff. The channel is not yet formed, right? Correct. So here is my let's say my gate material. This is my gate, this is my oxide. So this is n plus source, n plus drain. This is my channel length L. So tell me, will there be any capacitance present over here? Yes, here it will be. It will be here. Okay, it will be distributed here also. But there is no channel formed. So it will not be distributed across the source or the drain region. So these capacitances will be what? So in the cutoff region, there is no channel that is linking the source and drain. So CGS and CGD will be 0. So all these capacitances are what? These capacitances are CGB. Yes or no? And what will be the value of these capacitances? They are valid across the entire length of the channel, right? And the width of the channel is how much? You already know. How much is the width of the channel? W. This is W. So it's a big rectangle like this. Okay, whose length is given as L and width is given as W. So what will be the area? Can you tell me? It will be Cox. This will be Cox into W into L. Agree? Everyone? So that will be CGB. Are you understanding? Yes or no? Because there is this is the operation MOS in cutoff mode. So this is NMOS in cutoff mode. So in NMOS in cutoff mode, CGS and CGD are 0. The entire distributed capacitance, parasitic capacitance will be CGB, and that will be given by Cox into W by L. Cox because it is the gate oxide. This is the oxide thickness Tox. So there will be a capacitance here, metal plate and P plus silicon. Okay, and P plus silicon is body. Yes or no? So this is CGB, Cox into W into L. So this is what will happen in the cutoff mode. I hope you are following. Now next we'll go to the linear region. So in the linear region, how is the channel looking like? Can you all tell me? The channel is tapered like this. Yes or no? The channel is almost tapered. And this is my gate. Let me draw the oxide layer and the gate region. So this is my oxide, this is gate. So now tell me which, this is my N channel. This is N channel. So in the linear mode of operation, this is NMOS in linear mode. In a linear mode of operation, this is P silicon actually. Okay, if I want to draw it. So N channel isolates the P substrate from the gate. This is my gate terminal. Yes or no? So here it is my channel. N channel is there present between gate and this. So which are the capacitances will be distributed over here? Tell me. It will be 1. These will be distributed like this across the channel only. Okay, they will be connected to CGS or CGD. CGS or CGD, but none will be CGB. So here in the linear mode, CGB will not be present. Why? Because the N channel will effectively shield P substrate from the gate. Okay, to the gate to channel capacitance over here. The gate to channel capacitance is equally shared between source and drain. So this is called as CGS, will be approximately equal to CGD, will be approximately equal to half Cox W by L. So both of them are distributed equally, that's what we are saying. Understanding? So this is what will happen in the linear mode of operation. CGB will be 0, CGS and CGD will be half Cox W into L. Are you getting it? So this all these capacitances, gate to substrate, gate to source, gate to drain, are called as gate to channel capacitance. Gate to channel. So your gate to channel capacitances is CGS and CGD, and they are distributed equally, let's say. Alright, so this is what happens in the linear mode of operation. Now let us go into, so this is capacitance per unit area into area, which is W into L. Now let us go into saturation mode. So do you remember in the saturation mode, the channel length, the channel region is disappearing at the drain end? Yes or no? So here we have, if we draw the channel over here, it's disappearing from the drain end. Yes? So now if I draw the remaining part, that is the oxide and the gate. So this is my gate and this is my N channel. So tell me which capacitance will be present over here? Tell me. CGS, CGD or CGB. So there will be capacitance present only till this part. So all the capacitance, there will be only CGS present. Okay, whereas CGB is 0 because N channel isolates my gate from the P silicon, and CGD is also 0 because there is no channel formed near the drain region here, correct? So CGD is also 0 because N channel is shielding P substrate from the gate, and N channel is existing but does not extend to the drain, that's why CGD is also 0. Okay, so if I estimate this distribution of capacitance CGS, it is around 2/3 of the total capacitance, which is Cox W into L. So this we don't have the derivation for how it is 2/3, but it's approximately 2/3. The gate to channel capacitance as seen between gate and the source is approximated by 2/3 Cox into W into L. Okay, I hope it is clear now. Yes or no? Hello. So CGS is called as, let me just describe, gate to channel capacitance seen between gate to source terminal. CGB is gate to channel capacitance seen between gate to drain terminals. CGB is gate to channel capacitance seen between gate and substrate terminals. CGD is gate to channel capacitance as seen between gate and drain terminals. Alright. Okay. Now if I write this in a table form, what will I get? Let's say if I write this capacitances on one side and write this in table form. So this is capacitances CGB, CGD and CGS, and this is the total capacitance. So total capacitance will be all the parasitic capacitance ka addition. And if I write in the different modes, cutoff, linear and saturation, and I fill this table. So this is what I get. So here in cutoff, CGB is 0 in linear and 0 in saturation, and it is Cox into WL over here. Okay, CGB is present only in the linear region. Here it is 0, here it is 0, so here it is around half Cox W by L. CGS is present, it's 0 over here, half Cox W by L over here, and here it is 2/3 Cox W into L. Sorry, by L, it's into L because it's area, W into L. So we have written this from here. Okay, here it is. See, CGS and CGD is half Cox W into L for the linear mode of operation. See, it is over here. Saturation may we have only CGS, which is 2/3 of Cox W into L. Okay, so if I add them together over here, here I get total as Cox WL, here I get Cox W into L, and here I get 2/3 of Cox W into L. Okay, so this is what I get. So if you can note down the table, please note it down. So what is the minimum value of CG which is present? Minimum value is 2/3 Cox W into L. So you have a minimum gate parasitic capacitance when you operate the device in the saturation region, and the maximum value is Cox W into L, which is present both in the cutoff and in a linear mode of operation. Okay, so the takeaway point is, if we operate the MOSFET in the saturations, it will have lower parasitic capacitances, which is 2/3 of Cox into W into L. Okay, everyone understood? Now if I plot this on a graph, if I plot the same information on the graph, let's say that if I want to plot this on this information on the graph, let's say this is x-axis, this is VGS. Okay, let me mark here VT, this is VT plus VDS. Okay, let me mark these points. So below VT we have cutoff region, and above VT plus VDS we have saturation, let's say. So let us normalize this point as 1, this as 0.5, this as 2/3, 2/3 is 0.666, right? So this will be C upon normalized one, C upon Cox W by L. Okay, capacitance divided by Cox W into L. Okay, so if we normalize this, capacitance upon Cox into W into L, what do we get over here? This is my cutoff region actually. Cutoff, this is saturation actually, and this is linear region. This is linear region. Okay, so in the cutoff mode, which capacitance is higher? Tell me. Which capacitance is there? CGB, right? And it is 0 in linear and saturation. So I'll draw Cox W into L normalized is 1. Okay, so I'll draw it like this. Oh, I have to use a different color. So it is CGB I am drawing. So it is maximum over here, and it's almost minimum over here. Let me draw it properly. Okay, it is 0 here. So this is a graph of CGB. Now I want to plot CGS. So CGS is 0 over here in the cutoff. So let me mark it with green color. It is 0 over here in the cutoff. This is cutoff region. then it is 2/3 of Cox W by L in the saturation region. Here it is. So yeah, it reaches to 2/3 in the saturation region here, and in the linear region it falls down to half Cox. Okay, so it falls down to half Cox like this. Okay, so this is CGS. And what about the next one, CGD? So CGD is only present in the linear region, and that too it is half Cox W by L. Rest all the regions it is 0. See, so if I plot this over here, so it will be 0 over here, it will be 0 over here, and it will only start rising here. So here it is around half Cox W into L. So this is CGD. Okay, so this is the graph of variation of gate to channel capacitance, gate to channel oxide capacitance as a function of VGS. Okay, as a function of VGS. Okay, so this is also important. This will tell you which parasitic capacitances are having the effect in the cutoff, linear and saturation mode of operation. Okay, is this clear to you? Any doubts so far? Hello. So y axis is C upon Cox into W into L, and we have drawn the 3 capacitances present over here. Okay, now we'll solve one numerical. So small numerical to understand the minimum and maximum capacitance. So please write down the question. So if gate oxide capacitance, if gate oxide thickness, if gate oxide thickness Tox is 200 angstroms, active device area is 1 micrometer into 1 micrometer, find the minimum and maximum gate parasitic capacitance. Okay, so let's start. So what is given? W into L is given, 1 micrometer into 1 micrometer. So how much is that? 10 raised to minus 8 centimeter square. Yes or no? Tox is 200 angstroms. So 200 angstroms into centimeter is how much? 200 into 10 raised to minus 8 centimeter. Yes or no? We have to find minimum and maximum gate parasitic capacitance. So can you tell me, first of all we should find Cox, which is epsilon ox upon Tox. So here it is 3.97 into 8.854 into 10 raised to minus 14, and this is 200 into 10 raised to minus 8. So tell me, what is this answer? This will be nanofarad per centimeter square. Let me know this answer please. Yeah, how much is this value? Yeah, come on, calculate this and let me know. .97 into 8.854 into 10 raised to minus 14 divided by 200 into 10 raised to minus 8. So use your calculators and let me know what is the answer.
175 nanofarad.
Okay, it is 175. No point or something.
0.75.
Yeah, tell now. 175.75 nanofarad per centimeter square. That's correct. Divided by 200. Yeah, 175 nanofarad. That's correct. Now, minimum gate parasitic capacitance. So minimum CG is how much? Can you tell me what is CG minimum? What you have written last time in the table? How much is CG minimum from this table? 2/3 Cox into W into L, right? So calculate that. So it is 2/3 into Cox into W into L. So 2/3 of 175.75 into 10 is to minus 9 into W into L. W into L is how much? 10 is to minus 8. So how much is this number? So you will get into 10 is to minus 15 farad. So tell me the number. 175.75 into 2 divided by 8. Is it 117.17? Yes. Just confirm this number.
Yes, sir.
So do you know what is 10 raised to minus 15? It is femtofarad. Okay. Please mute your microphone, please. Yeah. So it is 117.17 femtofarad. Now CG max. Maximum gate parasitic capacitance is how much? Maximum gate parasitic capacitance is Cox into W into L. So it will be Cox into W into L, that is 175.75 into W into L is 10 is to minus 8. So how much is this? Yeah, 1 point, tell me. 7575 na, into 10 is to minus 15 farad. Yes or no? No, wait a second. How this is higher and that lower?
CG min is 1.17.
Oh yeah, yeah. That's what I was wondering. How it is so. So this is 1.17, 1.17 femtofarad, and this is 1.755. Now it is correct.
Yes, sir.
Okay, all right. So yeah. So this is the end of the lecture number 1. In fact, we have one more lecture pending. So you let me know if we can cover this today only in the afternoon, or we can cover it because we have to complete this. I'll show it to you. How much is that? So next part is we have to derive this value of junction capacitance and large signal equivalent junction capacitance. So we have to derive the expression for CSBJ, CDBJ, which is close to around 15 minutes of work, and here it is the value. Okay, then we have to derive it for small large signal equivalent junction capacitances, right? Because we have already found out this. See, these formula we know what is CGS, capital CGD, CGB, all this we know. We have to derive these formulas: CBD, CDBJ, CSBJ, area capacitance and sidewall capacitance. So that derivation will take around half an hour's time. See, this is the derivation. All right. So this we have to analyze it very carefully. So yeah, these are the formulas. This is what we will get at the end. So this will take around half an hour's time to complete, and after that we have to solve a numerical for another half an hour. So this is the numerical which is very important. Here it is, see. So whatever we have studied, we will apply it in the formula form, and then we'll calculate this. This also is important. Yeah, these type of numericals you can expect they can come in the exam. Okay, this information will be given to you top view, and you have to find out all these capacitances values. These all capacitances. So yeah, this will take around half an hour to 45 minutes time. Again, more. Okay, so we require one lecture of 1 hour and 10 minutes or so. So you want me to cover it right now or after some time, today in the evening around 6 to 7 or 7 to 8?